Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So today we are going to review the key points of Speech6, which is the audio coding. Okay, so let's move on. What are the learning outcome for this chapter? So the learning outcome for this chapter is, the first one is introduction to audio codings. The second one is audio coding standards. Number 3 is details of MPEG-1 audio codings and quantization and bit allocations, and number 5 is quality measurements. Okay, so let's move on. So the first one is the introduction to audio codings. As you can see from here, we are focusing on the audio, okay, not the speech but the audio. So of course there are different thing that there are two different compression strategies, which is the lossless and lossy. As the name implies, the lossless will target on the redundancy and the lossy will target on the irrelevancy. Okay, so anything that you cannot hear, you don't need to transmit. Okay, but for the lossless, so what's the difference? The lossless is used, what are the benefits of lossless? Okay, as you can see from here, lossless means there is no loss of informations. Okay, maybe this is used for medical purposes, okay, for law, for business purposes, and for anything that redo the acquisition will be prohibited. Like for example, you are trying to, for example, record the sound in the Mars or sound in the moon. Okay, you don't want to go back there and then to re-record. Okay, so that's why the lossless is important. Okay, so but the drawback here is the compression ratio is very low, only half. For example, if you have 10 megabyte of the wave files, okay, wave file, it can only compress up to 5 megabytes. Okay, so the compression is low, okay, only 50%. Okay, but what about the lossy? The lossy is perceptually lossless. So perceptually it is lossless. It means that you cannot hear the difference. Okay, you can't hear the difference. Okay, so you are thinking that it will be the same. Okay, but actually it's lost some informations. Okay, means that the one that you cannot hear, you don't need to transmit, or you may introduce some quantization noise. Okay, so this is for can be the compression ratio is very high. For example, from 10 megabyte you can go up to 1 megabyte, for example, or even lower. Okay, so the compression ratio is high. But again, the the key point here also, the bit rate is proportional to the quality. Okay, so let's move on. Let's move on now on the lossy. So what we see here, we base for speech, we have speech production model. If you know the LPC, then you can see that it can predict the speech, the human speech, in 10 coefficient, for example. Okay, but for audio it will be different, because the range of audio source is so many. You can have the human speech, for example, you can have the piano. Okay, you can have the let's say a wind noise, and so on, ocean noise, and so on. Okay, so it will be difficult to model each and one of the audio source. So what you can do, you use the human auditory system here. Okay, basically the concept of masking. If you go back to the previous chapter, you know the concept of masking. We have simultaneous masking and we have also temporal masking. So it began with the threshold of hearing. Okay, why is that? Because using the threshold of hearing alone, you can save some bit. Okay, so for example, here you have 50 hertz signals. Okay, you cannot hear the signal until it reach above 40 hertz. Okay, so you cannot hear the 50 hertz signal unless it is more than 40 dB SPL. Okay, SPL sound processor level, more or less it is like the amplitude of the sound. Okay, so anything here, then you just need a smaller bit here. Okay, so if your signal is below the masking threshold, then you can introduce quantization noise, means that a smaller bit is okay. So if it is below the masking threshold, you can say that a smaller bit is okay. You introduce the quantization noise. Okay, but when it is like this, for example, above the masking threshold, then you need to put here more bit. Okay, here you need to have more bits. Okay, in order to maintain the quality of the sound. Okay. And also from the previous chapter, also we know that when you have one signals, then the simultaneous masking threshold is changing. Also you can see here following the triangular shape. Okay, so means that previously you have here, for example, 250. This is 250 hertz signals. Okay, and you have 200 signal. Normally you can hear at the 20 dB. Okay, but due to you have the masker here, then it will mask the signal. So mean here you can introduce also small bit because you cannot hear the signals. Okay, so from here alone, then you can save so many bits. Okay, you can see here, if you put here, if anything below the masking threshold, you don't need to transmit, you don't need to save. Okay, or you don't need means also, in other words, also you just put the small bits. But whenever it is above the masking threshold, you need to have higher bits. Okay, in order to improve the quality. Okay, so as you mentioned here, the human ear is act like a band pass filter. Okay, the act like a compilation of filter banks. Okay, so you can see here filter bank number 1, number 2, and so on. Yeah. Okay, so for example, this is the spectrum. Okay, this is the spectrogram of one frame of the signals. So if you have some signals here, then you have frame by frame, and then one frame will be like this. Okay, so and for the introduction of audio coder, so what is the what you call the key point here? So you can see here, this one is the key point. Perceptual model means that we are using the human auditory system. Okay, so from this information, as I mentioned earlier, you can see from here, if you below masking threshold, you can introduce constant noise, so you don't need more bits here. You can remove some of the bits. Okay, so from the perceptual model, then it will control the quantization and coding. Okay, it will control the quantization and coding. Okay, so not for example, you can see from here. Okay, so for example, I have four filter bank, for example. Okay, so this one below masking threshold, so I can put less bit, this one less bit, and then this one is above masking threshold, for example, then I can put more bits here. Okay, so after the so this is the result is MP3, for example, or MP4, and then this is MP4, MP3 or MP4, and then this one is original, this one will be wave. Okay, wave. Okay, but remember that this is a lossy compression, means that this wave file and this wave file is different. Okay, because you have a lossy compressions. Okay, so let's move on to the next one, to the next learning outcome, which is the audio coding standard. Okay, so why do we need the standard? Okay, standard means so that we can play anywhere. Okay, so if I save in my computer, you can also play in the car or in other computers or in your music player or in your smartphone, for example. Okay? So that's why you need a standard. Okay, so let's start from the MPEG. MPEG has what you call so many standards. Okay, it go from video and also audio. So we'll be focusing on the audio. Okay, in our lecture. Okay, so MPEG has so many things. So start from MPEG 1, MPEG 2, MPEG 3, MPEG 4, MPEG 7, MPEG 21. Then after that you have also MPEG A, B, C, and so on. Okay, you can read here. Okay, so they are still ongoing standardizations. Okay, so this is MPEG I. Okay, 2020 immersive media. You can see the standard later on, but we'll focus here. Okay, so MPEG 1 have so this is the original MPEG standard. MPEG 1 has 3 layers. Okay, so layer 1, which is MP1, MP2, and MP3, and this one still being used for digital video broadcasting. Okay, or digital audio broadcasting. Okay, but remember that in the video, okay, in the MPEG you have also 2 components: video, audio, and the third one is the synchronization between this video and audio. Okay, because you don't want to have when the person talking and then this one is out sync with the audio. So you have also the third standard, which is on the synchronization or the integration between the video and audio. Okay, but let's move on here. So MPEG 2 is standardized on 1995. You have backward compatible. It just adds some lower and higher sampling frequency and add more channels. The details you can see in the lecture notes. And then this is the state of the art of audio coding. Any audio coding will be based on this one. Okay, state of the art. So means that you cannot compress more, you cannot compete with this AAC. Okay, because it's already compressed, it's already optimized. Okay, so this is the state of the art. Okay, MPEG-3 is drop. Okay, so that's why the layer .mp3 is not MPEG-3, because the MPEG-3 is drop. Okay, the .mp3 is what's it, MPEG-1 layer 3. Okay, so let's move on. And then we have the MPEG-4 scalability. So the reason here is this, you can read from the lecture note that you can have from the text to speech until the audio AAC. Okay, from text to speech, LPC, general audio, and then AAC. So if the if the source is speech signal only, the human speech only, then you can use LPC. That's why it is scalable. Okay, depends on the bandwidth. Okay, but if it is content music, then you can put the AAC. Okay, and continue. Okay. Beside the MPEG, also you have other things, which is, this is proprietary from Sony. This is from Sony. So attract 3, attract 3 plus, and attract advanced losses. So the last one is 2005. So some of the car audio, Sony car audio also can play this one. Okay. And the last one, of course, if you go to the cinema, you have the Dolby audio. Okay. So you can see from multi-speaker here. Okay, multi-speaker. Okay, so this is the standard. Okay, so let's move on. Okay, just forget about this one for the moment. So what are the next learning outcome, which is the details of MPEG audio coding. So here I'll try to explain in a short in the key points only, but we are going also to discuss MPEG-1 and mainly MPEG-1 layer 1. Okay, so what is the difference? So the A here is MPEG-1 layer 1 and layer 2. Okay, and this is MPEG-1 layer 3. Okay, so you can see what's the difference. This is the difference, and and this one is also the difference, so more complex. Okay, MP3 is more complex. Okay, so but the keyword here is the psychoacoustic model. So this is, we are using the human auditory system to tell the quantizer whether we have whether the signals is below masking threshold or above the masking threshold. So you can see here, this is from time, go to the frequencies. This is 32 subband filters. Okay, so you have here 32, 1, 2 until 32 subband. This is in frequencies. And in order to calculate the psychoacoustic model simultaneous masking, remember that you need to go into also the frequency. So this is FFT, time to frequency as well. Okay, then from there you allocate for each band. So from this calculation you allocate from each band whether the band is below the masking threshold or above the masking threshold. Okay, and then continue, you have the coded audio data. So in here it will be lossless. Okay, lossless compression, and here will be lossy. Okay, especially the quantizer, and here will be lossy. Okay, so what do we calculate? So we calculate remember that we have 32. So this one is from the FFT, so the output from here. Okay, we calculate the global masking threshold. Okay, and then from here it converted into 32. Remember here 32, so you have 0 to 32 here. Okay, 0 to 31 means 32 subbands. Okay, you calculate for each one is signal to mass ratio. Okay, so this is how do you read this graphic? Is easy. So you just, when you have the ratio, means in the log domain it will be signal minus mass. Okay, so if SMR is minus like this, means that the masking threshold is above the signals. Okay, so this one is below masking threshold. Okay, can you see? So this one is below masking threshold. What does it mean? It means that we can safely introduce quantization noise here, or less bit. Okay, and then but we need to have more bits here, the one that has higher SMR. Okay, so let's see. So for example, I have some original signal here. The signal is low pass noise plus 11.25. So this is 11.25 kilohertz sine wave, and the sampling rate is for 48 kilohertz, and this is the FFT point, 512 FFT point. Okay, and this is the original, and this is the coded. Okay, so the coded is this one. Okay, this is the coded. Okay, this is original. So this is, I'm using the MPEG 1 layer 1. So what you can see here, you can see the difference. If you don't see the difference, let's see here. Yeah, so you can see it, you can see the difference. Okay, you can see why you have here the blue one is all below here. It doesn't matter because you can see here this one is below the masking threshold. So if there is some difference, some much different, that's okay because you cannot hear it. Okay, so you cannot hear this part based on our calculations. Okay, and also here you can see the same representing this one. Okay, but here we need to preserve because this one is the error signal, and you can, when you see here, it's looks like you are calculating the triangular simultaneous masking threshold. Okay, and so on. Okay, so you can see from here the what you call the originals is the red one. Okay, and the coded is the blue one. Okay, it's not the same, but you hear is almost you hear it as almost the same. Okay, so you will hear it. Original is almost like the coded. Okay, means that you need to hear it, and then you hear the original, and you hear the coded one. It will be almost the same. Okay, based on your marking threshold calculation. Okay, so let's move on. So what are the next learning outcome, which is the bit allocations. So what we hear, so this is MP3 coding. So what you can see from here, the bit allocation takes the highest part. Okay, because you are doing the iteration here. Okay, you are doing iteration. I'll show to you in a simple way. Okay, so this is the simple way. As I mentioned earlier, you have the several subband from 0 to 31, or just to make it simple, I have 4 subband, 1, 2, 3, 4. Okay, and go to bit allocation, and then after that you will have the synthesis filter in the decoder. So this is analysis filter. Okay, and then you add this one, and you have the coded signals. Okay, so you are hoping that XN is as close as possible to the original signals. Okay. So let's see the first one. So say that we have altogether only 10 bits. Okay. Before I move, so do remember that we have this formula, right? 1 bit is equal to 6 dB increase in signals in SNR. So when you add 1 bit, it will increase 6 dB. But the first one, of course, you need to add 2 bits because you have you need to have the minus and plus. Okay. The 2 bits mean the first one is for the sign, and the next one is for the value. Okay, so sign, value. So that's why in the first one here you have 2 bits. Okay, so you see I allocating 2 bits. Okay, so let's see here. So what we see, this is for example the SMR. Okay, simultaneous masking ratio. Okay, as you can see from here, so what the algorithm do, it will try to find the highest SMR first. Okay, means this is the one that we need to preserve. Okay, the signal that we need to preserve. Okay, so what we'll do, then you allocate 2 bits here. 2 bits mean 2 times 6, it will be 12. So you have 28 here. Okay, and then the sort again, and this is the highest, 30. You allocate 2 bits here, become 18, and continue. Okay, so this one we can see here, we can allocate 0. If we don't have enough bits, then we can allocate 0. It doesn't matter because it is below the masking threshold. Okay, so you allocate here. If you have fixed bit, for example, you have 128 kilobit per second, then you will have 128 kilobits. Okay, every seconds. Okay, that you can allocate to each bit. So you can see this is part of iterations. Okay, you iterate here, that's why it takes long time. Okay, for the bit allocations. Okay, so again, this is based on the signal to mass ratio. Then it will allocate find the highest SMR first, then it will try to allocate the more bit here. Then after that, if you have more, if you have leftover, then you can allocate to the negative SMR. Okay, so let's move on. The last learning outcome is the quality assessment. So you can see from here, from our previous graph as well. So how do we do quality assessment? Okay, basically we have two things. Okay, we can have subjective evaluation and we can have the objective evaluations. Okay, so what we have here, so we have the original signals. Okay, we have the coded signals. Okay, so you can see from here, so you can calculate like original minus coded, then you can have some performance metrics. Okay, you can see whether it is close or not. Okay, but it's not that easy, because you need to have you need to consider the human auditory system, the masking and the effect of masking, simultaneous masking, and so on. Okay, so we have two type of evaluation, subjective evaluation. So basically we are using the listening test here. So you listen test here, you play the sound here, and then you listen. Okay, how then what do you put here? You play the original. This is always the original signal, and then this one is randomized between the original or coded. Okay, this is or can be coded or original. So this one will be randomized. Okay, then you, of course, if it is original, you can put 5. You can see, you can listen, compare between this one and this one. Okay, reference and the plate one here. Then you can compare the next one. If it is not good, then you can put 4 or less. Okay, then you will have something called subjective difference grade. Okay, so you can have original minus coded. Sorry, the other way around. Okay, coded minus original. Okay, coded minus original. Okay, coded minus original. So if your original is always 5, so if coded is 4, so your SDG is -1. Okay, so the subjective evaluation is the most accurate one, because at the end the human will hear the file. Okay, we'll hear the sound file, we'll hear the MP3. Okay, so this is the most accurate one, but this is time consuming. Okay, because I need to play here, and then it is expensive. Maybe you need to create a soundproof room and so on, use the high quality mic headphone and so on. Okay, so for algorithm development, there are something called PEAQ. So objective evaluation, basically you are using some mathematical formula or using some algorithms. Why is objective evaluation? Because this one is consistent. Okay, and it is very fast. Okay, consistent, fast. No matter how you run it, every time you run, it will produce the same value. Okay, every time you run, it will produce the same value. But in subjective, if you listen this one today, you might give different opinion on the following day. Okay, so that's why you need to have at least, for example, 30 people, and then average the score. Okay, so you can imagine that it is time consuming, expensive. Okay, but it is also more accurate. Okay, so the the PAQ has two two configuration, which is the basic and advanced. Okay, basic and advanced. So normally you just use this one, advanced, slightly longer. Okay, maybe you need this one need 1 second, you don't need 2 seconds. Okay, to run, but it will produce, still it is faster than you are doing the subjective evaluation. So it will produce the ODG. This is the SDG, subjective difference grade, and this is ODG. So the value is the same here. Okay, so if the same, so you have 0, -1 until -4, the same thing like this one. Okay, so this is basically the what we have here. Okay, so if you have any help, let me know. Okay, you can always go to us in the Telegram group, or on the mailing list, or in iTalim, and I'll see you soon, inshallah. Okay, assalamualaikum warahmatullahi wabarakatuh.